2021. Today's topic will be Clean Water Challenges and Opportunities by Professor T. Pradeep, Institute Professor, and Deepak Parekh, Institute Chair Professor, Indian Institute of Technology, Madras. And Professor Pradeep is actually also a Padma Shri Award winner, and he has also been recently appointed as Chairman Board of Governors in an extremely esteemed institute in nanotechnology. And this particular webinar series has been planned in with three important global themes. Plus, these global themes are also extremely important for our Indian subcontinent as well. And Professor Pradeep is one of the foremost experts in clean water technologies. And that is why we are starting this series with Professor Pradeep, who is going to speak about clean water technologies. And SIDDHI is a platform that is meant for creating a synergy between various stakeholders, and especially in themes relating to technology and rural development. That is why we are extremely honored to host Professor Pradeep, who is one of topmost names in India and also in the world in terms of clean water technologies and nanotechnology. And SIDDHI provides a platform for socially relevant technologies. And we also feel proud to bring academia, industry, experts, policymakers, government officials, NGOs, social entrepreneurs, think tanks, and the general public as well. And today's itinerary will be, just after my introduction, I will actually hand over the microphone to Professor Raghunathan Rangaswamy, Dean of Global Engagement, IIT Madras, who will introduce Professor Pradeep and the abstract of the talk, and then we'll hand over the mic to Professor Pradeep. The talk will be for 45 minutes, and after the 45 minutes, we'll have a Q&A by Professor Pradeep. And please post your question and answers in the Q&A box provided at the right-hand side of the screen. Thank you very much, Professor Pradeep. It's indeed a great honor to have you in SIDDHI webinar series on such an important day and also on such an important theme. Thank you very much. Over to Professor Raghunathan Rangaswamy. Professor Raghu.
Hi. Hi, Pradeep. How are you?
Very nice.
We are live. We are live.
Okay.
Please carry on, Professor Raghunathan Rangaswamy. Please introduce Professor Pradeep.
Okay. It's my distinct pleasure to introduce Professor Pradeep. I think he requires not much introduction at all in this country for the amount of research work he has done and the amount of socially relevant work he has done. And he has a long list of accomplishments research-wise. He is very well published, more than 500 papers. He's an institute professor, Deepak Parekh, institute chair professor. He's been conferred with several awards, the Padma Shri, Bhatnagar Prize for Research. He is the chairman of Institute of Nanoscience and Technology, and so on. So it's my real honor and pleasure to welcome here, and really thank you, Professor Pradeep, for accepting to do this for SIDDHI. We are very grateful, and we look forward to your talk. Thank you.
Thank you, Raghu. I'm thankful to Professor Sudarshan Padmanabhan and team for organizing this meeting, and my dear friend and colleague, Raghu, Dean Global Engagement, for facilitating it. Water is both a molecule and the mighty oceans. It is the moisture that makes dew and the glaciers. In this molecule, all subjects coalesce. It is both chemistry and physics. It is civil engineering as well as civilization outside. It is the concrete, it is the buildings, it is the bridges. They all stand because of the strength of hydrogen bonds. And if you are not sure about it, just heat a small piece of concrete to 250 degrees. You will find that everything will become dust. Water is us, and it is the planet. This is beautifully captured by this picture taken on December 24th, 1968, by the Apollo astronaut William Andrews. As the planet Earth is seen in the background of moon, we see nothing but blue. And that is water which Raman got inspired with. For all we know, there is no place in this vast space where there is as much water as we have. It's unique, and probably unique because of water. This famous picture that you see now was taken by Voyager as it explored the solar system and went beyond us. Well, as it went past Uranus, it looked back and took a last picture of the solar system. And this is what you see. And that picture prompted many, most famously Carl Sagan, to write his influential book with the same title, The Pale Blue Dot. I thought about, this thought about self-reliant, being self-reliant on a molecule, which is a universal heritage, is actually paradoxical. It is about self-reliance of water in India. Maybe it should be talked about from the larger perspective of the planet. And this self-reliance or equilibrium on molecules of this kind is realized largely from the context of carbon dioxide. And Svante Arrhenius, Nobel Prize winner of 1903, predicted global warming and the impact of carbon dioxide way back in this famous book, written originally in 1907 and translated in 1908. In this book, worlds in the the making, he predicted that without CO2, the world would be 21 degrees cooler. It took us nearly 80 years to realize that even today, many nations don't agree to this. And the impact of the invisible molecules is still being debated. It is, it is important to realize that it is probably because of the lesser impact of several other nations, several sort of unfortunate nations, less significant nations, that the world is safe today. Thinking about it, the Intergovernmental Panel on Climate Change said that control, I'm quoting, control over carbon emissions by developed countries is probably not the reason for the globe's survival, but the lack of development in less developed countries is. Well, this realization is easier today due to COVID. Remembering Svante August Arrhenius in this August month is interesting. Let me understand, let me place this in context. But as far as water is concerned, all our economic, social, and cultural outcomes, everything can be traced to water. Water, of course, is the simplest. And it is simultaneously the most complex molecule, and you will soon see that. And everything simplifies to water. And I would say that there is a water, or there is a price for water in everything that we do. And this has to come to our planning, and we will soon see that as well. So I'm setting this context here, looking at that larger water, starting from this molecule. Obviously, this is such a vast subject, and I hope I will be able to do justice to this in this lecture, although not completely. And when you start thinking about it, and thinking about it from India, many have said about water, and I took this particular quote from Mahatma Gandhi. The earth, the air, the land, and the water are not an inheritance from our forefathers, but on loan from our children. So we have to hand over to them, at least as it was handed over to us. This has been said in many, many ways, and there is a lot of innovation possibility in this. How do you recycle, for example, is an important question that comes out. And from a chemist perspective, the most influential chemist of 20th century, Linus Pauling, said this: life is a relationship among molecules and not a property of any molecule. And this is being increasingly recognized today in many different experiments. Let me take one or two very recent examples of science that is so exciting. And water continues to fascinate us, all of you know. This year, just a few weeks ago, we had this very nice paper saying that water can actually be elastic. So here is a tiny fiber of water. This is ice. And this is being pressed now. And as you can see, it is elastic. Just last week or 2 weeks ago, there was this paper in Nature saying that water can actually be metallic. And that is because of the electrons in a tiny thin layer of water. You're actually seeing the color that is of that water is being changed as you put electrons in it. And this happens because of the unusual nature of water, and that is being spectroscopically investigated here. So that apart, there are many exciting challenges in water. So looking at water today in this context, or in our discussion, we are talking about water, the liquid water, and the water that we consume. And I say this, or I would refer to this as clean water. This is not H2O in its purest form. This is water with a number of minerals that we consume, and that is our safe water within the safety limits of all the ingredients that we can have. So that water is very big, and water is as big as this, something like 10 to the power 18 tons of water on the planet. The important thing I mentioned about this in the context of Seventh Day Arrhenius. Arrhenius was originally, he was the first person to say that there is exchange of molecules between planet Earth and space. And he in fact estimated this. But today we know that the amount of water is roughly constant. Although a little bit of exchange happens, by and large it is constant. The precipitation is of this order. What is of importance is that India is safe. Looking at the countries, all the countries in the planet, average rainfall in India is 85th of the 186 countries, with Egypt being lowest and Colombia the highest. But India is getting enough water. India's water withdrawal, you will soon see, is far lesser than this number. So obviously, India is not at risk, but several places are at risk. Water is big in every scale, not only this particular number, but also in gaps, opportunities, wealth, and obviously the scientific, societal satisfaction it gives you. Water, as you look at globally, you find this huge issue of inequality. Globally, water is constant, but at places it is up, it is low and high. And that inequality is the reason for, by and large, the reason for poverty. And there have been a number of studies on this, and you are welcome to look at this. In that large context, every technology matters to ensure that everybody gets safe water. For this lecture, it is important to realize that world as a whole is not water stressed, and science, if we can do it well, we can ensure that everyone gets safe water. I was earlier referring to the water withdrawals, and looking at this picture of water withdrawals per capita, you find that all these so-called industrialized nations consume plenty of water. And that withdrawal is typically at this number. United States is somewhere around 1,200 cubic meters per capita. And India is somewhere pretty low, somewhere in this range, some 506 to 510 meter cube. So we are safe, well, considering the input that we get. But if you are in a position to preserve that water, we are safe. Water is also a huge issue of balance. And you get water essentially only from these two, and you have many risks associated with in the context of water, starting from global warming to pollution and many others. And everything affects life. If you look at it from a large picture, it is water and carbon dioxide that is this planet. Water and carbon dioxide making sugar and oxygen is the planet. And the reverse of it, sugar and oxygen going back to water and carbon dioxide, is us, the human beings, the animals. So this is our ecosystem. It is not that we produce only sugar, we also produce alkaloids and terpenes and many others. There are a large number of molecular species. You not only burn sugar, you also burn many others. But then what has happened is that for us to live, we require in the process of our living, not only us, animals as well, we produce just about 29 billion tons of CO2 per year. But because a human being, we produce 258 billion tons of CO2, an order of magnitude larger quantity. Along with that, we not only oxidize just sugar, we also oxidize many others. As a result, we have nitric oxide and nitrous oxide and sulfur dioxide and many others. And essentially, we have global warming. So we have opened up this loop, which was closed for a long time. And we will come back to this. This is where greater opportunities lie. And as a result, this circularity being so important, and that circularity is reflected in every sustainable development goal. In fact, 16 of the sustainable development goals have water in it in some way or the other. And I thought it is important to remember this in the institutional perspective. Thinking about water by safe water, that is not only an issue of safe water, pure water, drinking water, it's also an issue of wastewater. Look at that magnitude. Something like 1,000 billion liters a day. And this is what we produce globally. And we continue to produce more and more of this. We have several other issues as well. We have flood protection and pollution and many others. And it is important that the way that we have produced or expanded global urban area is essentially non-porous. I am aware of a lot of research that is going on in this context, but largely it is non-porous. And the way that we have produced or we have developed, we also put in a lot of energy into wastewater. The amount of energy that we put into wastewater is something like per person, energy per person per year globally is something like 2,800 megajoules per year. A huge amount of energy in terms of just heat, but there is also a chemical energy. You have all these chemical energies put into. So one wonders, is it not, why is that we are putting energy for wastewater processing? Why can't we process wastewater with the energy that is contained in it? A lot of innovation is required. I'm aware of a few things that are happening, but many more interesting challenges exist in this area. It is important just to look at the chemical input that is in water. For 9 billion people, nitrogen in wastewater would be of the same value or number as the anthropogenic production of reactive nitrogen. So all that ammonia synthesis that we are doing, which changed the world, the green revolution and all that, essentially is ending up in wastewater, and that we are simply losing. And that produces, or that gives a number of opportunities. Looking at it from a larger perspective, we also have to understand that the total water infrastructure value for a connected global population, forecasting it for a 9 billion people, that amounts to such a large number, $60 trillion. And where do you find this resource? This resource is just not possible to be met. And as a result, a prediction says that only 36% of the African population and 44% of the Asian population will be connected to a sewer network by 2050. It is important to, when you put numbers like this, 60 trillion, it is important to look at the global wealth. The total wealth of India is just about 13 trillion. And wealth of USA is somewhere around 130 trillion. And I was just taking the wealth of Kerala as a state, or many of our states, the number is in the range of 600 to 700 billion dollars. And this is one of those developed, so-called developed states. So we are looking at numbers so large, so huge, gigantic numbers. If you want to make sure that water infrastructure of a developed nation reaches everybody. Looking at clean water, largely from the context of this drinking water, you see that world as a whole is having huge inequality. And all the developed nations continue to have safe water, but many others don't have water, and the number can be as low as this. India's challenges are also huge, and many of these numbers are known to you. So therefore, let me not dwell into this, but look at the opportunities. 70% of the sewage is not treated. And our startup India estimate, this is somewhat dated, says that the opportunity there is somewhere in the range of $420 million. So this is really wrong number. And it is growing. So what I wanted to say is that there is a lot of opportunity. And this is happening in a country which is, all of these issues of water is happening in a country which is a land of rivers. But in that land of rivers, every river is polluted. Every river is contaminated. We have now data on most of them. And it is even more devastating to know that 50% of the microbial diversity is lost in most of the rivers. And globally, if you look at not just microbial diversity, something larger animals and things like that, You see that globally 83% of freshwater species have declined in the past 50 years. So that looks at a number of, or that presents a number of opportunities too. And this is that river Yamuna that all of us are aware of. Besides this, there are several other challenges. And this is a very famous picture that, you know, our groundwater depletion is so alarming that India will not have food at all. 67% of our irrigated land is, or 67% of our water for irrigation comes from groundwater in many places. And this is what happens in 2002 to 2008, NASA found this enormous decline in groundwater. So if you look at all of these in this perspective, well, water is declining, water quality is decreasing. Is there a hope for India? So let me relate this to this question of oil. When you ask this question, can we grow without water? It's like asking, can we grow without oil? Oil production peaked somewhere in 1970s or so. And this was the US figure. It's somewhere around, oil production was somewhere here at the peak. So it is called peak oil. But then even with decreasing oil output, GDP increased. And this can be seen in the context of water too. Water, there is this peak water. So this is all that you can produce. There is a peak in that. Sustainable water that you can extract, there is a limit to it. America did a lot of investment, especially the Clean Water Act and several other things that happened. And its implementation resulted in something very interesting. That is, the freshwater withdrawals essentially came to a constant number after 1975. Although GDP went on increasing, so you wonder what has happened here. This is because of a number of recycling technologies, a number of energy efficient processes, agriculture efficiency, and you will soon see all of these contributed to this. So there's a lot of technology in there. Of course, US has been is on the highest as far as water withdrawal is concerned, and so maybe it is not our example, but it's important to realize that it is possible to peak or to freshwater withdrawals can be kept at certain levels. If water is safe, population is safe. So life expectancy is high here in all of these countries when water is safe. And when water is safe, of course, per capita income is also high. So you can see that the entire world or a number of regions of the world stay somewhere here. And the task ahead is so big. From the context of water, looking at every Indian city, we have been getting reasonably good water. Chennai has been getting somewhere in the range of 1200 millimeters over water, rain. And it is, if at all, it is on the high side in the recent past. It's essentially been constant. And this is true of India as a whole too. And precipitation has been essentially good. But there are a huge number of challenges in the very recent past. So look at the climate change. And if I were to say the biggest challenge water is facing today is the climate change. And this can be understood very easily from the psychometric chart that you have. And if we have the temperature somewhere in this range, a tiny bit of change in temperature, the amount of water or humidity that is in the atmosphere is increasing, or it is much larger. And all of these can pour down in just 2 days or 3 days, contributing to the floods and whatever else. And this is on the increase. And if you were to look at this particular website, This catalogs all floods every day happening globally since 2014 or so. And you will see that every day there is a flood. And that washes away the entire wealth of certain regions, accumulated wealth of several decades in just 3 days. So how can you get back the get to the United Nations development goals if these were to be the realities? So the biggest challenge, of course, is therefore the climate change. And that is so alarming that in just these many years, what has happened to carbon dioxide and the effects of that is seen both on the surface of the planet as well as deep under the ocean. As you can see in this United Nations report, UNESCO's report of United in Science 2020, you will see these pictures, so alarming. It is also, water is also this issue of two sides of the, one side is floods, another side is drought. Both happen simultaneously. With all that, India is safe, or India is making progress. I was so pleased to see this of Jal Jeevan Mission July report, the June 2021, it says that it has these many functional household tap connections established. And several states like Telangana, Puducherry, and Goa already have 100% functional tap connections. Well, the numbers may be slightly different, but India is marching ahead. That is a very interesting thing, but it also presents a number of opportunities. Let me now switch to, well, I have in the remaining, whatever, 20 minutes or so, let me switch to something that is happening right here at IIT Madras. There have been a number of water purification methodologies, and we have introduced some of them with nanotechnology and nanomaterials. And I will briefly glance through these. Affordable clean water, I keep saying that it is a problem of advanced materials. Water itself is a problem, or water contamination is a problem of materials. Solution is also a problem of advanced materials. There have been new adsorbents, new sensors, new catalysts, new phenomena, many new devices, and I do not have time to tell you. All of these have been captured in several books and journals today. What has happened in the very recent past is that nanomaterials have become atomically precise, meaning that there have been a large number of tools that you can apply to understand the science that happens at that scale with atomic precision. So that means if you have a reaction or an adsorption or a process on a nanomaterial, you can study that in great detail. And here we are talking about atomically precise some particles of gold to understand model science, but need not necessarily be, the real materials need not necessarily be these. But this is to understand the science. But if you do that, what can you do? What can you accomplish? So we showed some years ago that nanomaterials of a particular kind, if you develop, it is possible to remove arsenic so affordably. And today we have arsenic-free water supplying to something like 1.2 million people at a cost of something like 2.1 paisa per liter, conforming to US EPA norms. So that is a great accomplishment. So what do we do? Well, look at a boy pumping water in this district, Nadia district in West Bengal. And this water is coming from a bore well. Water is coming from a depth of about 60 to 80 feet. And this pump, about 40-year-old cast iron pump, is set on this platform, cement platform. And you see the water that comes out gives you this stain of this red stain because of iron oxide. So in this region, if there is iron present in water, it's a sign, or it's a possibility that there can be arsenic. here, the arsenic that is present is 60 parts per billion, 6 times greater than the number that is the prescribed limit. So this boy pumps water, and one stroke of this pump gives you 300 ml of water, and we establish a small filter. Good thing is that with no additional pressure drop or no extra labor, with a contact time of about 2 or 3 seconds, you get clean water, and that you can get from this pump 1,000 liters or so per day. And this can run for 1.5 to 2 years at this arsenic concentration. And so this is fantastic. So the basis of all this is advanced materials, as I told you. What we do is we create metastable materials, which are metastable materials, are materials which are essentially not in their thermodynamic equilibrium. So you create such materials in confinement, nanoscale confinement. At that kind of, this kind of materials have enormous capacity for scavenging contaminants or for catalysis or for processes of whatever kind. And you create such porous materials and pass water through it, and you get clean water. So in this particular case, there are polymers, which are biopolymers, and you crystallize tiny flakes of materials, which are nanoscale. And you do this in such a way that you create porous entities. These pores can be, think about these as some matchboxes. And inside these matchboxes, which are nanoscale, you put nanoparticles of specific kind. We do this whole synthesis in water at room temperature, although the material that you get at the end, they are water stable. So this is almost like creating seashells. Seashells are made in water at room temperature, but you get extremely stable particles or materials at the end. They last for ages. So this is what we do. And in that process, there is no energy, electrical energy utilized, and there is no need, there is no contamination for water. And we introduce a concept that it is possible to create water positive materials. Most of the materials that we use in the context of clean water are materials which pollute water in the process of production, but in the process of utilization, they produce clean water. But after their life, they go back to soil and contaminate water. So the net outcome of these materials, as far as water positivity is concerned, is not significant. We wanted to say that we should create materials which are 2 orders of magnitude or 3 orders of magnitude water positive. 1 liter of water used for production, you create 500 to 1,000 liters of water, clean water, in their entire life cycle. So there are several aspects of science which I will not get into, and the key point here is that nanoparticles, if you use in science or in water purification, you can contaminate water with nanoparticles. So that is called nanotoxicity. So we study that in great detail. And if you deliberately add nanoparticles to a bacterium, you can do spectroscopy and show that it is nanoparticles really get into them. But with your material that we have produced, we can destroy bacteria, destroy viruses, remove contaminants, etc. But no nanoparticles outside, and nanoparticles don't get in because the nanoparticles are not released. So this is because of the nanoscale confinement we do, and particles are always in these cages. We create a number of materials. And when we do this, they are all small particles. They have very active surfaces. But in their confinement, you study whether they absorb species such as arsenic, arsenate or arsenite, and you do spectroscopy to understand this in great detail. And when you do spectroscopy in great detail, we understand for a given nanoparticle, how many such molecules, how many such contaminants can sit on the surface, and can you model these? And if you model these, you can, of course, do better and better materials. So today, we have materials with 20 grams or 25 grams of this material. You can pass arsenic-containing water through this, 100 parts per billion of arsenate, 100 parts per billion of arsenite. So arsenate and arsenite are two different forms of arsenic. And you pass it through, you have that combined concentration. What you get is less than 2 parts per billion. And you remove not only 1 or 2 liters of water, you run thousands of liters of water. So this particular material removes arsenic from 1,200 liters of water. So pretty large capacity. So you can create materials, some cartridges like this. You can do tests like that in the laboratory. You can take it to the field. So standard arsenic treatment plants supplying water for about 2,500 people. You have a plant which is sitting in some 40 cents of land area, typically using traditional adsorbents like aluminum. Now, because of this extremely large capacities and flow rates, etc., you can combine all these. This entire process can be done in a 3 cents land area. This large kind of reaction vessels or adsorption vessels, you can convert them to something smaller. The amount of water that is flown is 20 meter cube per hour. So something like 200,000 liters of water per day. And the input concentration is 168 parts per billion. And what you get is 2 parts per billion output. Essentially the same kind of capacities you can accomplish treatment. So that means you can implement it across. And these are all not arsenic. Some of them are different kinds of other contaminants like fluoride, uranium, etc. So you can implement smaller treatment plants or larger treatment plants. And the cost of this is now 2.1 paisa, as I just mentioned to you previously. So where is this going? Today, it is possible to monitor these arsenic contamination, etc., in real time. And treatment plans are coming with devices. And I have a short movie here to show you what we do. So what I told you is that it is possible indeed, affordable clean water, free of contaminants is just not a distant dream. It can be delivered. All that what is needed is for people to come together. There are a number of other technologies. So imagine if this were to be the whole country. That's about one state or a few districts of a state. How about for the whole country? That means you can get water quality on your fingertips. Today, technologies for all that is available. Affordable technologies are available, but many others are needed. So there are several places where water is not there. So how about atmospheric water harvesting? So we create materials such as these. These are nanofibers of metals by a methodology, and these resemble fibers on grass. So they condense humidity, and it is possible it is possible to extract water from air using such processes. So we have today a company which has water at 35 liters per day to about 2,000 liters per day. And that is a number of people have written about these. So it is possible that our ecosystem allows students to build organizations of this kind to take or water or anything else, which you will hear about later. Globally, this whole process, which today utilizes power, this is called active cooling technology. It is also possible that atmospheric humidity can be harvested by materials without no energy input. That harvested humidity in the nighttime can be released in the daytime by sunlight, and that humidity, of course, it increases the humidity in a chamber, and therefore that humidity will condense because the dew point is always somewhere close to the room temperature. So you can condense that humidity and thereby get clean water. This research is happening across, and in our institute also such research is happening. In addition, there are a number of other methodologies such as capacitive deionization. This involves removing ionic contaminants from water by applying a small potential on electrodes and collecting such ionic contaminants separately, just like reverse osmosis does. But here, the amount of water wastage is as small as 16 to 18%, not 50 to 60%. And energy utilization is also less. This can be run on solar and power requirement is low, so we have now a starter. Now, what is important to understand is that most of the Indian people, or in the southern India, so people live on this coast, and this coast, there is a lot of sunlight, and there is a lot of seawater intrusion. The water is brackish, and the brackish water desalination is very much feasible affordably with capacitive deionization. And so we have kiosks now installed at several places. There are several other developments in 2D materials, for example. So this is molybdenum sulfide. You can make nanoscale holes on these molybdenum sulfide single sheets. So exciting thing is that these holes, when you make, they are molybdenum rich holes. These are atomically precise, pictures of atomic resolution. And these molybdenum rich holes, such materials, if you expose to sunlight in presence of water, they produces hydrogen peroxide. So these materials produce hydrogen peroxide, and you can destroy organisms and bacteria and viruses. You can get clean water. If this is the input that is there, the output is there as far as bacterial concentration is concerned. And so tomorrow, it may be possible to create such materials. And we are not only working on this kind of disinfection, it is also possible to use these holes to create new kinds of membranes. Globally, there's a lot of other research that is happening. And this is a research of Rahul Nair from Manchester. He uses graphene for desalination and several other related processes. Such membranes can be controlled. Porosity can be switched on and switched off by electrical potential and controlled, and thereby new kinds of membranes become possible. There are friends here at IIT Madras as well as in other places. This I am taking from the work of Kanna Sureshan from ISER Thiruvananthapuram. He has developed extremely interesting materials which can remove oil from water. And I do not have time to show you this in great detail, but essentially it says that conventional materials, if you add them to oil containing water, you can remove some oil, but most of the oil remains. But these are new materials that he has developed, and they can remove that oil completely. And there are several other advantages to such materials. These materials can be applied on surfaces and harvest humidity sustainably. So a number of materials and technologies are available today, and some of them have been translated to products, as I told you in the context of the Amrit technology, or anion and metal removal technology, or atmospheric water harvesting, or capacitive deionization, and several others. Research is expanding. So with Rajneesh, we have a program on Clathrate Hydrates. So we have shown that it is possible to create Clathrate Hydrates even in extremely high vacuum, in vacuum as in space. And there are, of course, interesting possibilities with that kind of science, especially the kind of work of Praveen Linga from NUS. He's also a Vajra faculty at IIT Madras. He says that there is, of course, this kind of Clathrate hydrates under the ocean bed. You can take this or extract this. They contain methane as well as clean water. You can use the methane for energy, and at that time, you also get water, clean water, and you get water and energy simultaneously. So this is called hydrate-based desalination, and very interesting technology. Rajneesh is also interested. There are a number of aspects of science which are exciting. Analytical science is becoming, well, coming onto the mobile phone. This is electrochemistry coming to the mobile phone. And that electrochemistry can be done for the entire periodic table or all the compounds of the periodic table. And that would mean that entire water quality will be available for everybody. So spectrometers of this kind have been very big. For years, well, for some years ago, a decade ago, 2 decades ago, spectrometers were of this kind. But spectrometers today have come to this. And tomorrow, these spectrometers are going to be put on mobile phones, and we are developing such sensors wherein water quality is measured directly by spectrometers of this kind, and right from pipelines. So what that means is that every minute, every second, water quality is coming from every individual that produces this hydroinformatics platform and big analytics associated with that. And we are currently developing such analytics platforms for state governments. For example, this is something that we are doing with the state government of Punjab. In addition, this entire water resource infrastructure can be put on a digital platform, creating a digital twin of water resources, not only the quality, etc. For example, that gives you very interesting new challenges and new opportunities, such as the arsenic contamination that is there in now the entire state is mapped, and you can see how our contamination is changing temporarily, in the course of time. So this temporal evolution, the spatial evolution, is telling us new information. This is also telling us about new opportunities. Ultimately, all of these technologies have to be taken to field, such as this particular village. You may have a treatment plant that it is supplying clean water to this distant village. You are in a position to monitor many different things, including health-related contaminants and improvements, etc. But these knowledge should be replicated, and it should be used for other villages, other towns across the country. A number of policy interventions are essential in ensuring that water is safe for all. So science that, in the next 2 minutes, let me tell you a few things and close this lecture. Science, of course, can offer a number of things. Solve problems at source. There's a green and sustainable chemistry is the way to go. Water in agriculture. I talked only about water in drinking. There's a whole lot of water out there, and in energy and construction and many others. And several of our friends are working in IIT Madras as well. Water in materials. As detergents, plastics, and antibodies, and many others, antibiotics, wearable sensors, and big data give you a number of opportunities in this area. Water has to come to the central stage. So if clean water has to be there for India, I would say that we have to care for future. That means sustainability has to be there in planning and in the industry and the ecosystem, not only through sustainability goals that we have, but also in our thinking. Learn from the past. A lot of things have happened. Carbon in water purification is an Indian discovery from Harappan civilization. And so learning from the past, in ensuring water security, rainwater harvesting, conservation, and nature. Several other things exist here. Education has to happen, and water literacy is extremely low in our country. And critical knowledge in several areas. For example, we don't have our own membrane methodologies. Although we have a number of laboratories, we do not have something of our own in several areas. There has to be action. Recycling, protection. We have to cap freshwater withdrawals, maybe at certain numbers. And that needs action. Obviously, new initiatives have to be there. Water cost in products and services. How about an idea like national detergent policy? This is happening, but it has to come, and water has to be seen in every product. And I tell you, people ask this question, what do these opportunities in water amount to? I gave you this example of wastewater infrastructure for a connected planet at $60 trillion or so, comparable to half the wealth of United States. But you're looking at something as small as sensors market for water in India is estimated to be $1 trillion. So this is the market, this is the size that is available. I gave you a picture of a circular world with water and carbon dioxide on one side and sugar and oxygen on the other side. This world has really created all these problems for us. So it is possible that this food and synthetic food and several others that are here on the right side, you also produce cellulose, you also produce straw, you also produce sugarcane bagasse and many others. And all of these can go through biorefining. And several exciting possibilities exist, not only for alcohol from biorefining, but clothing and plastics and materials and detergents and fertilizers and many others. So it is possible, at least possible, that this entire thing can be carbon zero. The cycle can be carbon zero. And it is also possible that meat can be produced without animals. And that world will be very exciting with chemistry. The entire chemistry is done in water. Imagine that. And this is very much feasible, at least in several areas it has been demonstrated. Metal-free catalysis. Why should we use metals at all? Personalized medicine. Metals are not there, right? Personalized medicine is how it is going to be tomorrow. How about doing medicines or at that scale affordably? Synthesis tomorrow is going to be completely different. Already people have demonstrated this device called computer, where you just tell what molecule to be synthesized, just as PCR does or protein synthesizer would do. Molecules will get synthesized with specific chemical bonds. And that means no toxicity or reduced toxicity. A carbon neutral life is very much on the agenda, and water harvesting sustainably has to happen. And all of this would mean that one important science we have to focus on, that is the center, that is the sustainable technologies. And I know that there is this talk on energy technologies, but water and energy are essentially the same or two sides of the same coin. I told you the relation between this in some context, but probably in our Discovery campus, we should have a center for sustainable technologies where the cycle that I just told you about can actually be demonstrated. And we have this International Center for Clean Water to look at some of the challenges in the context of water at the IIT Madras Research Park. And my science has been done with a fantastic set of students, and only 1/3 of them do water, and several others do many different aspects of fascinating material science. Some of them have translated these technologies to products. They are owners of companies, and many people have gone out through the lab. Lots of companies and institutions supporting us in the larger context of ICCW. Many people have come forward And it has been possible to do all of these science because of IIT Madras, this great institution with Bhaskar at its helm, and several institutions supporting us. Thank you very much for listening to this, this talk. And I'll be happy to take questions.
Karthik, can you force some questions in the question answer box?
So Pradeep, there are many questions in the question answer box. So maybe you can, would you like to pick the more interesting ones and probably talk about it? There are lots of questions about, arsenic removal and so on, and whether it can be done at a home scale and things like that. So maybe that's something sort of a consumer question.
Just me take that first question, that you just mentioned. We do this at a scale of 1 million liters per plant today, to something like even 10 liters home units at that scale to 1 million liters. So there is, I think today scale is not an issue at all.
There are questions on climate change and so on, but I think that's more peripheral. And there are some questions about how there is a lot of non-uniformity in how pollution or water distribution and so on across the country, and how this can be addressed. So, for example, there are some rivers that are more polluted than others, and and also the inequity in rainfall distribution, inequity in basically everything. So, are there any strategies to counter that? General thoughts on that?
Well, all of these are very complex issues. So on the one side, agriculture is to be blamed, but without agriculture, we are not going to be there. Green revolution to be blamed, some extent, some people say, but without that, we are not here. There is a lot of subsidies, and subsidies have hurt us enormously in extracting more and more water and putting wrong fertilizers and into the soil. So many things. To give you one example here, and it's so complex a soup that one lecture is needed for that. But let me take one example. Why is that there is arsenic now in Tamil Nadu? Arsenic is there in Tamil Nadu. It shouldn't be there. And it is there in Bhavani River. And it is there in the entire, all these villages you see. And we have one person did a PhD on this, and not someone who was a doctor who did PhD on this. And we found this arsenic in our blood. Now, what is this? This is fertilizers. How did fertilizers come in? Fertilizers came in just because of our subsidies. How did this happen? Because we took the wrong fertilizer. Why did we take the wrong fertilizer? Because we wanted cheap fertilizer. Why did we take cheap fertilizer? Because of fertilizer subsidy. So if you start looking at this, you open up a can of worms. Now, it also opens up a number of questions about our holes in our entire policies. So it goes into something beyond our technical discussion. But I know that these are very important questions. So we should address them. And those of you who are listening, if you have concerns on this, we will be IIT Madras, and I am talking on behalf of several of our faculty. We would like to contribute our knowledge into this, solving the challenges. I would stop there and take the next question.
So, and somebody has asked about what are your thoughts on nutrient recovery from water?
Well, our dear friend Karthik, who is in Colombia, is extracting nutrients from water, an IIT Madras product. And so there are several people who do this thing. And our effort in India is also picking up. It is possible, at least in limited sense. In communities such as these, it is possible to do. But in a larger context, can it be done for Chennai city? Yes, there are people who talk about these. Now that is probably, if you start looking at the economics of it, at this stage right now, there are conflicting views, and I do not want to get into that argument, but it is certainly possible that in communities such as these, it is very much possible, and for which our own expertise is available and people are willing to help us also.
There's one question about plans for how in space what are the challenges in converting for example human urine and so on to clean water and things like that. So would you want to talk about that? So that is because, and there's also is a lot of these discussions about, I think it's Bill Gates' pet project as well. Right, so having a waterless toilet and the things like that. But there's a lot of water-related water purification challenges that exist and so on. So, any comments on that?
All of these water is an extremely price-sensitive thing, extremely price-sensitive. And if you are not there at that price, no technology is going to be there, whatever you talk about. And I do not believe that subsidy is the way forward as far as water is concerned. While that may be required in a short time window. So therefore, is it really possible to have complete recycling at a cost that is affordable, which I kept as 5 paisa per liter? Today, it is, I would say, a lot more innovations are required as far as wastewater to clean water is concerned. But wastewater to industrially processable water, yes, this is possible at that scale. And this is what we are doing, and IIT Madras is doing. My dear colleague Liji is well versed with that. So there are a lot of examples here. But coming to taking that all the way to potable water is one step further, and that is where new innovations are required. Capacitive deionization is one such. Nano bubbles is another such. Ozone is another. New kinds of materials is another. So all of these collectively have to come together in that context.
So wonderful. So I think I'll probably go with one last question. So you've been talking about how it's important to scale these activities, and these activities may have to be conducted at different scales, at say a single home to a community to a larger city or a state and so on. So what could, for example, a community like IIT Madras, I think we're doing a lot in terms of wastewater treatment, but what kind of an example could we set, and what is it that people can learn from our management of water?
Collectively, we have a huge gap that our learning and the societal needs, there is a huge knowledge divide that exists. If I were to look at Indian institutions per se, I mean, not just IIT Madras alone, combined knowledge of all of us in clean water can do great things for India. But there is no way that we have cataloged all of these. We have not showcased all of these. And all of these, this is happening largely because here in institutions, these are by and large faculty efforts. There are 100 things that a faculty can do, but there are 1,000 things expected. So this is where the larger challenge is. And we need to build institutions which are connecting in this institutional knowledge to societal requirements, especially the collective knowledge, because we are not good at everything around water. And as my talk would have said, there are 100 technologies. So by doing this, I'm sure we have good enough solutions that can be implemented in that sector that you mentioned. That knowledge, collective knowledge, the returns are substantial. And this is how nations have changed. This is how Singapore has changed.
Okay. So I think with that, we would really like to thank you for a characteristically engaging talk. And really, I mean, you could just see the number of questions and the audience engagement. We had, I think, close to 700 folks today. It's really wonderful. Thank you, sir. Thank you very much for spending your time. And I think talking about something is really topical, really exciting. And I can see even there are some school children who had posted some questions and things like that. So there's a lot of people who have.
I would say that please do write to me. I'm sorry that all of these questions couldn't have. I mean, I couldn't take all of them. At the time, I thought that I would speak for 45 minutes, but I spoke for 50 minutes. I didn't spend enough time on questions. So please do write to me. I will be glad to respond to you.
Thank you. Thank you so much, sir. So, and we have, this is only the first in a series of very exciting webinars. So tomorrow we have Professor Ashok Jhunjhunwala, another eminent speaker, eminent scientist, who's going to talk about India's energy needs and innovative solutions. So please do tune in for that. And the day after, we have our director, Professor Bhaskar Ramurthy, who's going to talk about India's 5G standard, the manufacturing ecosystem and impact. So these again are very, very topical, very, very exciting, and a wonderful way to celebrate the first anniversary of our SIDDHI webinar series, where we've been getting a lot of exciting speakers who engage not just with academics and the industry, but even with the public at large. So it's been a wonderful series. So thank you all for tuning in today, and do tune in for tomorrow and day after as well. We already have a huge number of registrations. And with that, I'd like to close with thanking our team SIDDHI, with Professor Raghu, our Dean, and Professor Sudarshan, who's been coordinating the SIDDHI webinar series, and our entire team, Ujjwala, Edil, Naresh, and Rudra. Thank you all, and see you tomorrow.
Thank you, Professor Pradeep. Thank you very much.
Thank you very much, sir. Thank you, sir. Fantastic.
Very nice. Please do share, the recording.
Definitely, sir.
Sure. It's already on YouTube. So we'll share the links with you.
Right. Thank you.
Thank you. Bye.
Sudarshan, I really enjoyed it. Thank you very much.
Thank you very much, sir. Thanks for doing it. Yeah.
Thank you. Thank you. So people came from, I think, all over the world, I suppose.
Yeah, we'll get those statistics. We'll share those with you.